Hi Y12, let's have a look at your paper 2. So it's got SL and HL questions in here as well. So let's have a little look at question 1. So this was also SL's question 1. A student investigates the EMF and internal resistance of a cell. The current and the potential difference are measured out of the terminal of the circuit. For this circuit, V equals EMF minus IR. The table shows the data collected by the student. The uncertainties for each measurement are shown. So then you're given the data table. You can see the current is plus or minus 1 milliamp. The voltage values are plus or minus 0.02 volts, and then you've got a graph here. So the first thing you are asked, if I pull this down, sorry, is the student has plotted error bars for the potential difference. Outline why no error bars are shown for the current. So if we go back to what the graph looks like, and also our absolute uncertainty values, 0.02 volts as a proportion of the voltage values that we have are visible, but 1 milliamp out of 97 milliamps is going to be far too small an error bar to be seen, so we're not going to see anything here. So all we need to say is that plus or minus 1 milliamp is too small to be seen on this scale. Okay. So then it says, determine using the graph the EMF of the cell, including the uncertainty for this value. It's because this is a paper 3 question that I've put into your paper 2 to give you some practice. If we go back to the original bit, they actually give you the equation, so they're not testing your memory here. And then if we look at our graph, hopefully you can see, V is the y-axis and I is the x-axis. So the EMF is going to be the plus C, and the minus R, because we've got the minus sign here, is going to be the gradient. I might make that a little bit bigger so you can see that actually. So we've got V is EMF minus IR. I can rearrange that to say V is equal to minus IR plus the EMF, and now that clearly follows Y equals mx plus c. So we are just looking for our y-intercept in order to find the EMF. So we're going to need to draw our best fit line first. There's a little range that you are allowed with this one. So ideally you're going to go through all of the points. Let me line that up a little bit better. Okay, so you can see my line of best fit is either going through all my points or all of my error bars. And I'm going to say that the EMF, which is when the current is 0, is 1.6 volts. So I've got papers everywhere here. But also notice that you have to include the uncertainty, you have to have the correct number of significant figures, and you have to have the value, all for 3 marks. So you would have got 1 mark for noticing that the value is the y-intercept. Okay, so that was worth 1. You would have got 1 mark for your EMF being in the range of 1.59 to 1.61, so they give you a little bit of flexibility with your line of best fit there. And then you get 1 mark for then stating your value of your EMF plus or minus your absolute uncertainty, which is going to be the same uncertainty as all of your other voltage values. So then you just write EMF is 1.6 plus or minus 0.02, and you can actually give your EMF to 3 significant figures, so I need a 0 here if I've chosen 1.6. And then it says outline, but notice that it says without calculation how the internal resistance of the cell can be determined from the graph. So this is where we go back to our equation and we say, okay, we've got V is equal to minus IR plus E epsilon EMF. And we know that we've got Y here, we've got X here, we've got plus C, so therefore the minus and the R is your gradient. So M is equal to minus R in this case. So what we need to say for the 2 marks is to say the internal resistance is equal to the negative of the gradient. And that will get you the marks. So it's noticing that 1, it's the gradient calculation you need to make, and 2, you need to take the negative of it. So question 2, we've got, if I pull this down, sorry, a ball of mass 0.25 kilograms is released at rest, from rest, at time t is 0, from a height h above a horizontal floor. The graph shows the variation with time t of the velocity v of the ball. Air resistance is negligible, therefore we've got constant acceleration due to gravity, and it tells you to take that as g equals minus 9.80. I think they allowed 9.81 if you use that value because it is technically more correct, but just notice in the question when they tell you these things. The ball reaches the floor after 1 second, so we've got an object that is falling under constant acceleration, so we can use SUVAT. So h is obviously s, so we've got SUVAT. We don't know s. We know that u is 0 because of the fact that we're told that it starts from rest. We know that a is minus 9.80 and t is 1 second because that's how long it takes to reach the floor. So we don't have a v value, so you can see that if we have these ones, we're going to say s equals ut plus a half at squared. But u is 0, so this part cancels from your equation. So s, which is h, is just going to be 0.5 multiplied by 9.8 multiplied by 1 squared, which is just 1, and that's just half of 9.8. So let's think about this. We get 4.9 meters for 1 mark there. Then it says label and the time and velocity graph using the letter M at the point where the ball reaches the maximum rebound height. Okay, so let's think about what's happening here. At this point, 0, 0, the ball is at its highest position. It then accelerates at 9.8 meters per second squared until it hits the floor, at which point it's instantly going to change direction. And so we see that by a change from negative velocity to positive velocity to show it's changed direction. So this section here is the point at which it is hitting the floor and changing direction. And then it says, using the letter M, label the point where the ball reaches the maximum rebound height. Okay, so we know that this is the section where the ball is rebounding. It has its maximum velocity. This point here is actually as it's leaving the floor, and it's going back up now because it's going to slow down, isn't it? It's going to have its maximum velocity at the point where it hits the floor, and then it slows down to rest at its highest point again. So it will reach its maximum rebound height at the point where it comes to a stop at its highest position in the air. So you want to label M at 1.6. Okay, and then it says state the acceleration of the ball, if I come back down, at the maximum rebound height. Okay, there's no air resistance, so at all instances the ball has its weight, mg, and therefore the acceleration is g. okay, because the weight is a force is mass times acceleration. G is always going to be 9.80. Okay. Draw on the axes. Now this could be a little bit confusing. I'll mark it either way because, sorry, it was on this page, but you've got another set of axes here. Hopefully you realise that. A graph to show the variation of the time. Let me come in a bit closer so I make it a bit bigger. Draw on the axes, a graph to show the variation with time of the height of the ball from the instant it rebounds from the floor until the instant it reaches maximum rebound height. No numbers are required. Okay, so we're looking at it leaving the floor and coming up to its highest position. Let me move this out of the way. So, we know that initially the height's going to be 0, okay, because it's at the floor. We also know that at some time later it's going to reach its maximum height. What we need to think about is how this graph then changes. We know that the acceleration is constant, okay, and it's going to be minus 9.80 meters per second squared, okay. It's going to slow down to a velocity value of 0 at this point. If the acceleration is constant and it's acting down, we know that the velocity, which is now in the upwards direction, is going to be decreasing in value. So if the velocity is getting smaller over time, then the distance travelled per unit time is going to get smaller and smaller. So our gradient, which is our velocity, needs to decrease. And it needs to decrease to 0. Now, if I were you in the exam, I would actually draw myself a little dotted line just to show the examiner that I know it reaches the horizontal, just so that they can see that you've ended your gradient horizontally. In part C it says, estimate the loss in the mechanical energy of the ball as a result of the collision with the floor. So I'm going to need to pick up a piece of paper from the floor. So, first things first, it tells us it's mechanical energy. Okay, so that's energy to do with movement. So we know that what we're looking at is the kinetic energy change. Okay, so we're going to write our kinetic energy equation, which is a half mv squared. Now, we know the mass, which was 0.25 kilograms, and then we need to look at the change in the velocity squared. So if I look back at my graph, okay, I can see that over 1 second, if I'm accelerating at 9.8 meters per second squared, at 1 second, this value is going to be 9.8 meters per second, but negative to show direction. And we can also see that after it rebounded, it went off in the other direction at 5 meters per second. Okay, so we know that the V value went from 9.8 or minus 9.8 meters per second to 5 meters per second from the graph. Okay, now we're only interested in the absolute magnitude because kinetic energy is always positive, so the minus sign really doesn't matter. Okay, so we can say that the change in kinetic energy is going to be a half m change in v squared because these two are constants. Okay, so we've got equal to 0.5 for the half. M was 0.25 kilograms. Oh, thank you, phone. Ignore that. And then our change in velocity squared is going to be 9.8 squared minus 5 squared. I've run out of space in the box, but not to worry. Therefore, when I plug that in the calculator, I get 8.9 joules of kinetic energy lost. Part D asks you to determine the average force exerted on the floor by the ball. Right, we've got to think about this one carefully. I haven't seen your papers yet, but I am going to imagine that many of you do not get all of these marks because you haven't thought through the forces. So, if this is the floor, and this is the ball, and it's just sat on the floor, we know that the ball has weight mg, and therefore we know that the floor has to exert a normal reaction force up to prevent the ball from falling through the floor. That's just in a stationary situation. Okay, so at all cases, the floor has to exert R at a minimum. Now, in addition to that, the ball in this case is actually falling, hits the floor and rebounds. So there's a change in momentum, delta P. Now, we know that the force exerted on an object when it changes momentum is equal to the change in momentum over the time. Okay, that's from when we looked at our Newton's laws. So we actually have two forces to consider. We have the weight of the ball that the floor has to account for, plus the floor has to account for the ball's change in momentum as well. There's a force exerted there. So we're going to add these two together to get our average force that has to be exerted. Okay. So we know that change in momentum is mass multiplied by change in velocity. I know that this occurs over how many seconds? I'll have a look at that in a minute. Let's just do our change in momentum first. I'm trying to get carried away here. We know our mass is 0.25. We know that the velocity change went from minus 9.8 to 5. So in order to find the total change, remember momentum's a vector, so now the minus sign matters. We have to add these two numbers together because we have to get from minus 9.8 up to 0 and then 0 up to 5. Okay, and so this is going to be 9.8 plus 5. I'm then going to work that out. I've done that already. When I do that, I get a value of 3.7 kilogram meters per second. So that is my change in momentum calculated. I'm then going to have a little look at the time it took for that to happen. So I'm picking the graph up from the floor again. So let's have a look. The rebound started at 1 second and it ended at 1.1 seconds. So the collision between the ball and the floor took the difference, took 0.1 seconds. It wants to get not blurry again. So therefore, to find my force, I'm going to do my 3.7 kilogram meters per second change in momentum over the 0.1 seconds that took. And obviously that is just the same as multiplying by 10, so we've got 37 newtons here. Okay, and we know, let's label that as P, we know that Fw is going to be mg. The mass of the ball was 0.25. G in this case for this question is 9.8. I'm going to get 2.5 newtons roughly, if I call that 10. Therefore, Fw plus Fp is the sum of these two. So I get 39.5 newtons, and that is my final answer. Now I'm going to predict that lots of you work this one out, but forget to add the weight. Okay. Then the last part, I think, of this question, is suggest why the momentum of the ball was not conserved during the collision with the floor. Well, if momentum has not been conserved, there must have been an external force acting. So you just want to say there was an external force. Exerted on the ball. Now you want to specifically say that that force was exerted on the ball because it asks for the momentum of the ball, not the momentum of the floor. There we go. So that's question, was that question 2? Oh yeah, it was question 2, sorry, I've lost track here. Okay, question 3. Let me zoom out a little bit. Was also SL question 3, so far the questions have lined up. So two loudspeakers A and B are driven in phase and with the same amplitude at a frequency of 850 Hz. Point P is 22.5 metres from A and 24.3 metres from B. The speed of sound is 340 metres per second. Okay, deduce that a minimum intensity of sound is heard at P. So the first thing is we want to find the path difference between the waves that are arriving from A and B. So that's worth 1 mark. So path difference is equal to 24.3 minus 22.5 is 1.8 metres. That gets you 1 mark. You then want to work out how many wavelengths that is. How many wavelengths fit into 1.8 metres? So I'm just going to do a quick calculation up here. We know that V is equal to F multiplied by lambda. The wavelength is what we're interested in, which is V over F, and we're given both of those values in the question, so it's just 340 over 850, which works out to be 0.4 metres, which is a helpful thing to have worked out. So now we want to see how many of these fit into the path difference. So 1.8 over 0.4 gives me 4.5 wavelengths. Okay, so in this section we have 4.5 wavelengths. That gets me 1 mark. Therefore, the wave, the point of the wave from A that meets at P with the point of the wave from B is going to be half a wavelength apart. Okay, because we have a full number of wavelengths here, we have an extra half of a wavelength factor consider. So therefore, we're going to get 1 mark for saying the waves will meet 180 degrees or pi radians out of phase at point P. That gets me 1 mark. And therefore I say destructive interference occurs. Okay, and we know that because that's our condition for destructive interference, where waves cancel each other out if they meet half a wavelength apart. Okay, in B, a microphone moves along the line from P to Q. PQ is the normal to the line midway between the loudspeakers. The intensity of sound is detected by the microphone. Predict the variation of the intensity detected as we move from P to Q. Now we just worked out that P was a minima. Okay, you can hopefully see that Q is directly in the middle of A and B. So we know that at Q we have our central maxima, just from our understanding of interference patterns. Okay, so we know then that this is because we've got a path difference at this point of 4.5 wavelengths. At this point, there is a path difference of 0 wavelengths. Okay, the length travelled from A to Q and B to Q is the same. Okay, so there's no path difference. So if this is at 4.5 wavelengths, in between Q and P, we must have 4 maxima, where we have path difference of 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths. Okay, so we've got a couple of things that we can say for our 2 marks. Okay, between here we will see equally spaced minima and then maxima. Okay, we'll obviously see our minima in between the 2. So you get 1 mark. I'm going to put it over here so that we can still see the diagram, but obviously you've got space on the next page for saying between P and Q there will be equally spaced maxima and minima. Okay, that's worth 1 mark for recognising. You could get 1 mark for stating that there is the central maxima at Q. And you could also have gained the mark for saying there will be 4 maxima between P and Q. Okay, so it's only going to get you 2 marks, but if you said any of those, you'll get a mark for each. Okay, so this empty space up here was just for that question, so let's go straight to C. When both loudspeakers are operating, the intensity of the sound recorded at Q is I0. Loudspeaker B is now disconnected. A continues to emit sound with unchanged amplitude and frequency. The intensity recorded at Q changes. So remember that Q was in the middle of A and B, and we know that at any point waves will add as a vector sum. So we know that if we've removed B and we just have A where they originally met in phase, we now have half the amplitude. A has halved. Okay, because we have one source instead of 2, which we had before. Okay, now we know that intensity is proportional to amplitude squared. So if A has halved, then we've got a factor of a half squared change for our intensity. Okay, so I is going to be 1/4 times smaller, because 1 squared is just 1, 2 squared is 4. Okay. So IA is the new value over the original. So the ratio is this value. It's just 1/4 is your final answer there. Okay, question 4. Let's have a little look at this one. So we've got 2 equal positive fixed point charges. So Q here and Q here are 44 microcoulombs. Again, don't make the mistake and miss your power of 10. And point P are the vertices of an equilateral triangle of side 0.48 metres. So we've got some distances, 0.48 metres here. Okay, show that the magnitude of the resultant electric field at P is 3 meganewtons per coulomb. Alright, I'm going to take the field of one of them first, and then I'll add the second one. We know these values of Q are the same, okay, and we know that by definition, electric field strength is force per unit charge. Okay, now because these charges are the same, and we're equidistant from both, we know that actually whatever field we have from here, we have the same in magnitude from here when we're at point P. What I can do is I can split, if I think about the field pattern, now remember that it's radial from positive charges, so if you imagine the other field lines, and they all point away because they're positive, and we've got the same over here. Okay. Now we know that we've got an angle that we can work out because we have 2 lengths of our triangle, and we know that it's an equilateral triangle. So we know that this is going to be 60 degrees, we know that this is going to be 60 degrees, and we know that this is going to be 60 degrees. Okay. So what we're interested in is the electric field strength at point P. So we're looking at the field line from the charges to the point P. Now, an electric field is a vector. Okay, field strength is a vector, so I can express these field values in vector components. So I can split it into the vertical component, which in this case is obviously going to be upwards, and I can express it in terms of the horizontal component. Okay. Now hopefully you can see that because both of these are positive charges, that the horizontal component of the field from this Q is going to cancel with the horizontal component of this Q. So there's no horizontal component when you are directly equidistant from both of them at P. Okay, but you can hopefully see that the vertical component is in the same direction, so they're going to add together. Okay, so first things first, we're going to work out the value of the field. Okay, we're going to use the fact that we also know that field strength is equal to kq over r squared. Okay, so when we are at this distance r, so when r is 0.48 meters, the electric field strength from one of them is going to equal k, which is 8.99 times 10 to the 9, multiplied by the charge, which is 44 times 10 to the minus 6, because it's microcoulombs and come across, over that separation distance squared. Okay, now when you do that, you get, I've done this on the calculator earlier, a value that looks something like this. Okay. Now I know that if that's the value of the field strength from one, I'm also going to have to add it from the other. So I'm going to do two lots of that value. Okay. But I'm only interested in the vertical components, remember, because the horizontal component of that value cancels. Okay. So that's our magnitude, but we need to do, if this is 60 degrees, then this is 30 degrees. I need to find the vector component in the vertical plane. So I need to multiply by cos 30. Okay, and when I do that, I get a value that looks something like this, which I can say is 2.9, well, 3 really, times 10 to the 1, 2, 3, 4, 5, 6 newtons per coulomb. Okay, and that is equal to 3 meganewtons per coulomb. And so I've proved it there. And then it says, state the direction of the resultant electric field at P. Well, hopefully you can already spot that we know it's going to be vertically upwards, because we've got this vector plus this vector. The horizontal components cancel, so what we're left with is upwards, so we're just going to write upwards. Okay. It says point P is now moved closer to the charges. A point charge Q of minus 2 microcoulombs and mass 0.25 kilograms is placed at P. When X is small compared to D, the magnitude of the net force on Q is F is approximately 115x. And it says, explain why Q will perform simple harmonic oscillations when it is released. Okay. We know that for simple harmonic motion, acceleration is proportional to minus x. And if mass is constant, which it is, then the force must also be proportional to minus x. So the force is proportional to the displacement in the opposite direction. Okay, so let's have a look at our diagram. We place our point charge at P, okay, and it's negative in value. So what we have is a negative charge at this point here. If this is our equilibrium line, then displacement x is upwards. Okay, so displacement is up. But remember that the field lines, which at the point where I'm at P are going to look like this, the field lines represent what happens to a positive charge. Okay, a positive charge will be pushed away this way and this way. But we have a negative. Okay, so remember that because we have a negative charge, it's attracted to both of these. So it's being pulled downwards. Okay, so where before we said upwards vertical component, we know that the force is going to be in the opposite direction in this case because it's a negative charge. So when my x is up, my F is down. Okay, the force on this negative charge is going to be downwards because of these two positive charges. And so I can see in this situation, I do have F is proportional to minus x. Okay, and so the 2 marks just come from writing that in words and saying the force is proportional to the displacement. okay? And it's directed back towards the equilibrium position. Now, even if you hadn't understood the context of this question, if you're asked to explain why something will perform simple harmonic oscillations, this is all you have to write. Okay, calculate the period of oscillations of Q. So this one might have been a bit trickier. So we have our simple harmonic motion equation, A is equal to minus omega squared x. We also know, that that is equal to force per unit mass. Okay. Now we are told that the force approximates to 115x. Okay, so I can say that this is equal to 115x over the mass, which I'm told is 0.25. Okay, so if that is equal to minus omega squared x, hopefully you can see that this x and this x are going to cancel. And I now have a value for omega squared. Okay. Omega squared then is equal to 115 over 0.25 in value. Don't worry about the negative sign, remember that's just to indicate that the direction of the force. That is equal to 4 lots of 115, which is 460. Therefore, omega is the square root of 460, which works out on my calculator to be 21.45. And we know that by definition, our angular frequency, omega, is equal to 2 pi over t. I can rearrange that because what I'm looking for is the time period t, and that's equal to 2 pi over omega. So I'm just going to do 2 pi over my 21.45. And that gets me a value of 0.29 seconds. Okay, question 5. Just a little bit so you can see a bit more. An ohmic conductor is connected to an ideal ammeter and a power supply of output voltage V. You've got some data, so you've got the density of free electrons. Now that's a number density, a number of electrons per centimetre cubed. So in our equation that's m. We've got resistivity, rho, 1.7 times 10 to the 8, minus 8 ohm meters, and then you've got your individual dimensions, and it tells you the ammeter reading. So this is I. So first things first is we want to calculate the resistance of the conductor. So the equation that we're going to use, because we don't have a voltage, R is rho L over A. We know our density because we are given that. Sorry, not density, resistivity. Sorry, brain not on point this morning. So we have our value there. So that's our 1.7 times 10 to the minus 8. We have our length. We just need to look to our third one. But don't forget to put that into meters. And then our area is going to be this multiplied by this. So it's just this squared. So 0.02, excuse me, 0.02, but we're going to convert that into meters first, all squared. And when we do that, we get a value of 0.043 ohms. Okay, so you'll be getting 1 mark for recognising which equation to use and 1 mark for remembering to convert to meters there. Then in B it says calculate the drift speed V of the electrons in the conductor in centimetres per second. This is important to spot because all of my values have been given here in centimetres or per centimetre cubed that are helpful to me. So I don't need to convert any numbers here. So I've got my drift speed equation, I equals NAVQ. In this case, because it's electrons, Q is E. So I can rearrange because I'm looking for my drift speed V. So V is equal to I over NA, and in this case I'm going to put E because Q is an electron. I'm told that my current is 2 amps. I'm told that my density of free electrons is 8.5 times 10 to the 22. My area is, again, I'm going to keep it in centimetres when I multiply these by each other because I need it in centimetres per second, so it's just 0.02 squared multiplied by the charge on an electron, which is in your data booklet, which gets me 0.368 centimetres per second. But also notice it's worth 3 marks. I need an appropriate number of significant figures. If you look, all of my values have only been given to 2 significant figures, so I can't be more accurate than that. So therefore, to 2 significant figures, I have 0.37 centimetres per second, and that gets me my 3rd mark. Okay, question 6. This is SL question 5. We've got an electron moving in circular motion in a uniform magnetic field. The velocity of the electron at point P is 6.8 times 10 to the 5 metres per second in the direction shown. So we've got a V value and we've got a B value given because we're told the magnetic field is 8.5 teslas. State the direction of the magnetic field. 1 mark. So, firstly, notice that it tells us it's an electron. Okay, so in order to work out the direction of our magnetic field, we need our left-hand rule. So therefore, we need F, B, and I being linked together. Now, if the velocity of an electron is to the right, my current is to the left. Okay. This is circular motion. Okay, the circle is shown, so therefore at any point, and I'm at point P, my force has to be towards the centre of the circle. So now I can work out the direction of B because I know the direction of the other 2. So I have my left-hand rule. Sorry, I've got loads of pen ink all over my hands. So we've got current middle finger, my blue tipped finger, to the left. We've got the force acting up the page. So hopefully you can see that my green tip finger, which is my magnetic field, is pointing out of the page. Okay, so out of the page. And then it says calculate in newtons the magnitude of the force acting on the electron. So values that we have, we're going to use F equals BQV. Because we have the fact that it's an electron, so we know this, and now we also know this, so we just plug our numbers in. So 8.5 multiplied by the charge of an electron, multiplied by the velocity which we're told. And when we do that on a calculator, the value we get is 9.2 times 10 to the minus 13 newtons. So a pretty small force, but remember it's an electron, which is also tiny. CI, explain why the electron moves at a constant speed. So now let's have a little look. There's no work done, there's no kinetic energy gained, and that's because the force and the velocity are at right angles to each other, and we know that work done is Fs cos theta, and cos of 90 is 0, so there's no work done in the direction of the velocity. So all we want to say is the force is at 90 degrees to the direction of travel. So no work is done. Okay, so that's for 1 mark there. And then it asks why it's a circular path. So again, if it's a circular path, we have to have a centripetal force. And the condition for a centripetal force is that the velocity must be at right angles to the magnetic field. So we get 1 mark for saying, well, because the velocity is at right angles to the magnetic field, 1, therefore we have a centripetal force acting. Also so 1 mark. Okay. So, question 7. A satellite powered by solar cells directed towards the Sun is in a polar orbit. The satellite is orbiting at a distance of 6,600 kilometres. This needs to be converted into metres for our equations to work. And it says, determine the orbital period for the satellite. So, we know that we have a centripetal force keeping it in orbit. And we know that that is being provided by the gravitational attraction of the Earth. So we can say that the centripetal force, mv squared over r, must equal gmm over r squared, our gravitational force. So our centripetal force is being provided by our gravitational force of attraction. Okay, so if I pull r up and m down, the m's cancel and one of the r's cancel. So I can say v squared is equal to gm over r. V is therefore equal to the square root of gm over r. Okay, so I'm going to work that out first. My orbital velocity is going to be the square root of g, which is 6.67 times 10 to the minus 11, multiplied by the mass of the planet, which we're told is 6 times 10 to the 24, over the distance to the satellite, which we're told is 6,600 kilometres, so times 10 to the 3. If I find the square root of that, I get a velocity value of 7,787 metres per second. Okay, now I know that my time period is going to be equal to the total distance travelled over its speed. And the distance travelled is the circumference that we're working out here, where the radius is the r value. So we've got c is pi d, so 2 pi r over the velocity. So we've got 2 pi multiplied by our 6,600 times 10 to the 3 over the velocity value that we just worked out, 7787, and when we do that we get a value of 5325 seconds. Okay, so you're going to be getting 1 mark for equating these two forces and rearranging to get an expression for V, 1 mark for finding the expression for your time period, and then 1 mark for your final answer. In C, it says, not all scientists agree that global warming is caused by the activities of man. Outline how scientists try to ensure the agreement on a scientific issue. So this is your how science works question. So remember when I made you look at articles and I made you look at how scientists collaborate and things like that? That's why I've made you do that, because you need to be able to answer these questions that I cannot predict. So you could have said that in order to make sure that we have global agreement on issues, you could either have said work is peer reviewed, would get you 1, or you could have said full details of experiments are published, so that they can be repeated again. Now the worst answer I saw on the mark scheme, I personally wouldn't give you this, I think it's a bit too vague, is that they allowed you to say international collaboration occurs. I personally prefer the top 2 there. Okay, so question 8. So this is SL question 7. The diagram shows the direction of a sound wave travelling in a metal sheet, not to scale. Particle P, also I should point out the fact that they put that in bold tells you that you shouldn't expect your answer to look like it does visually in your mind because of the diagram. So particle P in the metal sheet performs simple harmonic oscillations. When the displacement of P is 3.2 micrometers, the magnitude of the acceleration is 7.9. Okay, so it's simple harmonic motion. We know that A is proportional to minus x. So I can say A is equal to kx, so therefore A over x is a constant. Okay, I'm given an initial displacement and acceleration, and then a final displacement, so I can just use my proportionality to get my answer. So I've got A1 over x1 equals A2 over x2. So initially, when the displacement was 3.2 micrometers, I had 7.9 over 3.2. I'm not going to worry about the micro because it's just a ratio. Must be equal to the new acceleration over 2.3. So therefore, A2 is equal to 7.9 over 3.2 multiplied by 2.3. Sorry for running out of space. And therefore that is equal to 5.7 meters per second squared. It says the wave is incident at a point Q on the metal air boundary. The wave makes an angle of 54 degrees with the normal at Q. It gives you the two speed values in the different media, and it asks you to calculate the angle between the normal. So we'll use Snell's law. N1 sine theta 1 equals N2 sine theta 2, and the fact is N is equal to the ratio of C over the velocity in that medium. So I can express this as C over V1 and this as C over V2. The C's will cancel, so I can also say 1 over V1 sine theta 1 equals 1 over V2 sine theta 2, because remember there would be C's here and here, but I can just cancel them because they're on both sides. Okay, so it says calculate the angle between the normal at Q and the direction of the wave in the air. So it's asking you for theta 2. Okay, so I'm going to rearrange and say sine theta 2 is equal to V2 over V1 sine theta 1. I'm told my velocity values. Air is the second medium, so that is V2. So that's going to be 340 over the initial velocity, which was 6010, multiplied by sine 54, because that was my initial angle of incidence. And that gets me sine theta 2. So if I do sine to the minus 1 of this on my calculator, I'll get theta 2. So theta 2 actually works out to be a ridiculous number of 2.6 degrees, which is why they've told you it's not to scale, so that you don't panic when you see this number.